Hi there, this is Jacob Nash Engineering Lessons, and this video is on Unit 1.3, Lesson 1, Introduction to Thermodynamics. Now, if you notice, if you watched any videos from Unit 1.1 or 1.2, I had this kind of like crappy thing that took forever because I couldn't type on it. Now I'm on my Windows computer, so it's kind of hard to write, but I still am able to do this video, and still I think my handwriting might come out better than on that tablet that kind of was messed up that I was using. And I may be able to transfer to my iPad that I'm getting in a few weeks, but this may just work for the rest of the videos that I make. But anyways, so this is on Introduction to Thermodynamics, and it's probably easier, like this video is going to be a lot better than any of the other ones I've made so far for Principles in Engineering, because like you can actually see what I'm saying. So first, what is thermodynamics? So let me see, I can do blue. And also, with the screen recorder, like if you ever use ShareX, you should get that. It only works for Windows, unfortunately, but it let me only record this thing. That's why you can't see what color I click on and stuff. So, there you go. Thermodynamics. This is the study of the effects of work, heat flow, and energy on a system. So that's pretty straightforward. I mean, like the definition is what it means. There's no more to explain than that. That's the components that it covers. Then thermal energy. It is kinetic energy in transit from one object to another due to temperature differences, and this is measured in joules. Remember, joules, it has a J for its symbol, and yeah, this font makes the J's terrible because it doesn't have the thing on the top, and I've said that in a different video. I's and J's should look like this. They should not look like this, because you could think that's a L. So yeah, coming from someone with one of those letter names, you can tell. Then temperature. Well, we know what temperature is, but the literal definition is the average kinetic energy of particles, not the total amount of particles, just the average kinetic energy of the particles. Now, there's three different types of units that can be used for temperature that you may have to convert to through the formula sheet that you were given, or is online if you weren't given it. And first, we have the freezing points and the boiling points. So freezing point of Celsius, or is 0 degrees Celsius. Then 32 degrees Fahrenheit and 270 degrees Kelvin. That's what the K is. So you most likely know, you may know all of these, but you probably at least know either Celsius or Fahrenheit, because that's probably what's used where you live. If you're in the United States, you might use Fahrenheit. If you're in the United Kingdom, you might use Celsius. Really, I use Fahrenheit, but it seems like that Celsius makes more sense in the first place, because 0 is freezing and 100 is boiling. But anyways, like I just said, 100 is boiling, then 212 for Fahrenheit and 373 Kelvin. Notice that there's not a degrees for the Kelvin, it's just K. You don't do degrees K. Then absolute 0 is when all kinetic energy is removed from an object. That could mean that there is 0 K. 0 Kelvin. And 0 Kelvin equals negative 273, negative 273 Celsius, degrees Celsius. And then what it would equal in Fahrenheit, you could convert yourself, but I'm not going to do that right now. Then there are different laws of thermodynamics that are listed. So the 0th law, which when you first hear that, you might be like, what in the world? Why? What is 0? Why isn't it just first, second, third? I don't know. Ask the person who made these laws, but whatever. So the 0th one is if two systems are found to be in thermal equilibrium, which the definition from PLTW is when two touching objects in a system reach the same temperature. Well, I mean, it doesn't have to be two, but that's just an example. The system would then lose its ability to do work once it's in thermal equilibrium. But anyways, back to the law. If two systems are in thermal equilibrium with the third system, then the first two are in thermal equilibrium as well. Meaning, let me click on this. So system 1, 2, 3. If 1 and 3 are in equilibrium, 2 and 3 also are, then 1 and 2 have to be as well. That's what that means. The first law of thermodynamics states that thermal energy can change form or location, or can be increased, but it cannot be created or destroyed. So I already said that in the last unit in terms of just energy in general, but still it applies to thermal. So this just means that like you can't create energy, you can't destroy it. And you might be like, what? You create energy? Like if you think about a hydropower plant, like energy is created when it goes through that. Well, not really. It just changes form to a more visible form to what you know. It's not created. And it can't be destroyed either. But it can change form, location, or it can be increased. The second law of thermodynamics is probably the most simple of these three, and it is that thermal energy flows from hot to cold. So if you see that asterisk pizza example, there's an example by PLTW that says, like, let's say that you just have a pizza, and that would be a terrible rotten pizza if it was black, but because that would be either burnt or I don't know, rotten. But anyways, that's because I don't feel like clicking on the colors. So let's say that you touch a frozen pizza. Well, yeah, it's actually that would be you pointing with your pinky finger if that's what it was. Let's try that again. You touch a frozen pizza. Is the thermal energy going to flow from your hand to the pizza or from the pizza to your hand? It's going to flow from your hand to the pizza because your hand at that point is warmer than the pizza because it just came out of the freezer. And you can feel the thermal energy flow when you touch it. That's why it feels cold on your finger. Now, if it just came out of the oven, then it will flow from the pizza to your hand because the pizza is then warmer. And if the pizza could feel, it would feel thermal energy and like the difference because but really the energy would then be flowing from the pizza to your hand in that case. Now this next term the definition of this one is the measure of how evenly distributed heat is within a system. That's straightforward also. Then convection and conduction, that's important. Convection is the transfer of thermal energy by movement of fluid. The fluid expands and then rises when heated. This is like if you took earth science, like you know how convection works under the crust. Warm air rises always, and then cold air falls. This was always easy for me to remember because I had to sleep on a triple bunk bed with my other two brothers. Because I have 4 sisters and 2 brothers. And I'm on the top, so it's always hot up there. And then on the bottom, it's cooler. But that's how I can remember that, because the heat rises. That's why it's hotter on the top bunk. Then conduction is the transfer of thermal energy within an object or between objects. I don't know why that says objects. That's just a typo. I don't know why that. I guess I tried to type from too soon or something. From molecule to molecule. So spoon soup example. So let's say you have a bowl of soup. Hot tomato soup. How about that? and then you have a spoon here, it's resting on it, and it's hot. So I'll do this to show that it's hot. Now, there's conduction occurring right here because the spoon is sitting on it. That's occurring. Then there are conduction equations. Oh, sorry about that. So the equations, well, first, before I even say them, you should know what certain variables mean in this case. This will be used, this part might be confusing to you, but it will make sense once we actually solve the different examples. So, we have first Q. This is energy transfer. Oh, great, now that looks like O. I'll put it a little lower. Energy transfer measured in joules. So it's important that you know what it's measured in, because your teacher's not going to like it if you come up with your answer for energy transfer and then you just put 111,243, but it's supposed to have joules on it. Then lowercase m is mass of the material in kilograms. You may have to convert. If they have it in pounds, you're going to have to convert to kilograms. Hopefully your teacher will give you that factor. If not, you can look it up. Like what is 1 kilogram equal to 1 pound? Like, but I mean, you also could just look it up and have the work do it yourself. But your teacher probably wants you to write it out yourself, so you can just see how many pounds is in 1 kilogram. So then C is specific heat capacity. It has no unit. It is given to you. So this is just a certain number for each component that you have. Like if you have aluminum or nickel or copper, it will be given. And if the case for water is, I think, 1484. Let me see. No. 4,184. I got that backwards. That's what it is for water. Then P is the power, or the rate at which energy transfers, and watts. That's the same thing as last unit. Then delta T. Change in time in seconds. Now, if you're like, oh great, another random Greek letter. Well, sorry, that's just how it is. There's lots of Greek letters that you use in this course, as well as other engineering courses. Delta, you probably have even used in algebra if you took it. Delta y over delta x is slope, but delta it means change in when it's used in equations. It just means change in. That's why it's change in time. If you took away the delta, it would just be time. Then, so notice that's a lowercase t. This is an uppercase T, and it means temperature. And the unit could be in Celsius, Fahrenheit, or Kelvin. And this is in seconds, if I didn't say that. You might have to convert from minutes to seconds. That one is really easy. If you had 10 minutes, you would have to multiply by 60, then you would get 600 seconds. And why 60? Because there's 60 seconds in a minute. Then lowercase k is thermal conductivity. Now the unit for this is written strange here because I didn't know how to type an equation, but let me rewrite that. I mean, not equation, like fraction. So the unit for thermal conductivity is very strange because that's what it is. It is joules over seconds times mass times degrees Celsius. And you might be like, oh my gosh. Because at first glance, you might think that's part of an equation. You don't need to know what joules or seconds or mass or Celsius is. That's a unit. It's not something you solve for. It's not part of the equation. So just take note to that. That's what you would put at the end. So if you got an answer for thermal conductivity, once you used one of these equations, and you got 119, you would put the unit as 119 joules over seconds, etc. And then here are the equations. So the one for energy transfer, there's Also, another one that's used, but not in this video, but I'll explain it in a different one. But there's kind of a little, like, song to remember about that equation, and that I know. I don't know if your teachers told you that. So Q equals M times C times delta T. Yes, that's uppercase, or the teacher will slap you in the face. Well, that's not even on rhythm. Sorry about that. But if you heard what I said, Q equals M times C times delta T. That's what it is. Then, because it's not delta times T, because it's not change in times time, because change in is not even a number. The time is the number, but it's just changing. And then, yes, that's uppercase, or your teacher will slap you in the face. Hopefully not, or they'd go to jail. But that's just to help you. That's just so that it would rhyme. And uppercase T, because if it's lowercase, that's seconds, and that would make the equation invalid. And here are other equations. I'm not going to say them out loud, but we will use them in the next video. Then the next 4 videos, lessons 2 through 5, will be on different types of equations, or I mean examples, like word problems to solve for. There's one for finding. Let's see. Well, there's one about R value. There's one about finding thermal conductivity. There's one for finding the total, or the final temperature. And then there's also one for finding, well, net energy transfer, or just, yeah, that's Q, and we would use P times seconds T, like the lowercase t, but that doesn't matter right now. And you'll have to learn a new equation in that video, which is Stefan's law, which, that thing, I'm telling you, that's probably one of the most complicated things, but we'll get to that, I'm assuming probably on lesson 5. But anyways, thank you for watching. I'm sorry that this was a long video, but I had to explain a lot of things, so at least it's less videos for you to watch. And I'll work out those kinds of problems in the next videos. Thank you for watching.